Hey, so welcome everyone to this week's seminar. We're very happy to have Rama Cont from the University of Oxford speaking this week. Rama is a professor of mathematical finance at Oxford. His background is he has an undergraduate degree from École Polytechnique and a master's in theoretical physics from École Normale Supérieure. He was a researcher at École Polytechnique and also had academic positions in Columbia and Imperial. He's won several prizes, including the Louis, I have to read my handwriting, Louis Bachelor Prize from the French Academy of Sciences, and an award for excellence in interdisciplinary research from the Royal Society. He's also a fellow of STEM. So it's a great pleasure to introduce Rama, and this week he's going to talk about asymptotic analysis of deep residual networks. So over to you, Rama.
Thank you very much, Matthew. And as you will see, this builds on previous work by Matthew, so I'm especially glad to speak in this seminar, and I hope that we'll get some feedback on this. So this is joint work with Alain-Sam Cohen at InstaDeep, which is a deep tech company based in London. Alain Rossier, who is a DPhil student in Oxford, and RenYuan Xu, who is at the University of Southern California. Sorry, this page should be updated to reflect her new affiliation, but she used to be here in Oxford. And the paper, there is a short version of the paper which has been published in ICML, and a longer version which includes more mathematical details, and especially the last part, we're going to put it out soon. Okay, so here's the outline of what I'm going to present. I'm going to briefly go over deep residual networks. Many of you have heard about this probably, and neural ordinary differential equations. This has been a topic which has excited a lot of people over the last few years and got a lot of the community in stochastic, in optimal control interested in the link with neural networks. So I've spent a few minutes on that. And then I'll go deeper into the relation between these two objects and the asymptotics underlying deep residual networks, and how these asymptotic regimes can be described. And so I'll show you first some numerical experiments exploring the asymptotic behavior of these networks, and then I'll show you some mathematical results describing the various asymptotic regimes that we have been studying for these networks. And at the end, I'll show some links with stochastic optimal control. Okay, so what are residual networks? So residual networks are a variation over multi-layer neural networks. So these are feed-forward multi-layer neural networks in which we introduce what's called a skip connection at each layer, meaning that we so in a multi-layer neural network, you have an input at each layer, call it X, and then there's a weight. So there's a linear transformation and a fine transformation applied to the input. And then these outputs of the layer are sent to an activation function, in this case ReLU or something else, and then there can be an additional layer applied to the output of the activation function, and this is the output of the layer. In ResNets, you add the input to this output, so you get what you have in a feed-forward network plus the input of the layer. So in some sense, you have at each layer, you have identity plus something. Something is what you would have in a multi-layer feed-forward network, and you add the identity. So why would you do that? Well, if if you're an analyst or if you come from numerical analysis, well, you know that identity with identity plus something, and you iterate a transformation that is identity plus something, you can approximate a lot of objects, a lot of semigroups. So this seems to be a flexible idea. And in fact, it seems to also work very well in applications. Well, initially, the people who who devised these architectures, they don't notice that, first of all, you can learn the identity trivially because you put all the ways to zero. So representation of identity is trivial in this architecture. And so now if you want to learn something, there's a perturbation of identity, then you can play with this identity plus the residual. And then you basically only need to learn the residual. And if you can break up the global map into a product of identity plus somethings, then again, you can learn these residuals in a way that is more stable but numerically. And the main argument for being interested in these architectures from the application side was that they work really well in many applications, including image recognition. So there's this study of He et al. 2016 on ImageNet, which showed that deep ResNets are competitive, are state-of-the-art in terms of image recognition. These are graphs taken from their paper. This is a very well-known and well-cited paper. And in this case, deep means 34 layers, something like 50 layers. We're not talking about millions of layers, but still, what you see is that they have a very good performance compared to other architectures. Also, another point of interest, which I'm not going to talk about here, maybe at the very end, is that deep ResNets, through this parameterization of each layer as identity plus something, they address indirectly the issue of the vanishing or exploding gradients in deep learning. So we're talking about the vanishing or exploding gradients of the loss function with respect to the data or with respect to the hidden states. And that's because you basically formalize, you parameterize the transformational learning as identity plus something. So this avoids this vanishing or exploding gradient. Okay, so that's also one argument which is cited a lot. So they have good properties empirically. They have very good performance. And so what are they? Well, if you haven't heard of this before, it's really not very complicated. Many of these ResNet architectures. So, I mean, I gave you some examples, but so the whole idea of adding the identity can be superposed on any architecture, multi-layer architecture. Really can be a CNN, can be convolutional, can be feed forward with fully connected. So I'm not going to, I mean, in the paper, we do discuss different architectures, but here I'm going to just fix the ideas here. I'm going to look at this parameterization, which by choosing flexibility weights can embed several of these architectures. So basically the idea is you have a forward dynamics for the hidden state. You input some at the first layer, you input some data X, and then at each layer, you're going to do the following. You do an affine transformation with these weights AK and BK, shift and multiplication. So these are all matrices. The hidden state is a vector, and then you apply the activation function, some nonlinear activation function, and then you can post multiply by some other weight. So these weights delta K, AK, BK are trainable. And that's the forward dynamics of the hidden state. The hidden state at the last stage will be the output, or you can do a linear transformation at the end, or some classifier transformation, some threshold at the end. So that's what's done in a lot of these architectures. So you iterate this L times, where L is the number of layers. And as I said, there are these trainable weights at each layer K. And you have some activation function, which is really a one-dimensional activation function applied component-wise. So why is this so exciting for many people? Because it was noted by Chen et al. And Haber and Rutoto in 2018 that, well, this looks like the Euler scheme for some ODE. And what ODE? Well, if you think of the delta L in front as a small step size or small parameter of the order of the step size, then this could be the discretization of the following ODE, or for some where you now think of it as a deep network limit, where now either layer becomes a fictitious time index, and then the time flows from 0 to 1. So you normalize by 1 over the number of layers, the time step, and this time flows from 0 to 1. The input is at time 0, and then the output is at time 1, and the hidden state evolves according to these dynamics. So if you do a Euler discretization of this with step size 1 over L, you will get this with delta L equals 1 over L. Now, what's the interest of this? Well, of course, this gives us some information about how these networks could possibly behave when the number of layers increases. That's always something of interest in these deep networks. What's the role of the depth and so on? And this could be a possible description of the deep network limit for this architecture. And also in these references, they're actually more interested in the practical consequences of this, one of which can be that, instead of doing back propagation or forward propagation in this way, you can actually use a state-of-the-art solver for this ODE, and actually you can solve for the gradient of the loss function with respect to the hidden state. Instead of solving it through back propagation, you can solve the adjoint equation as you do in optimal control. And more generally, this has led to a large interest in the literature, because then once you see the limit as an ODE, then the learning problem becomes an optimal control problem for this ODE. And there's a lot known about optimal control of ODE. So you can use interesting algorithms that are state-of-the-art algorithms for solving the optimal control problem, which then may lead to a more efficient learning algorithms if indeed this ODE is related to the learning problem for the ResNet. But does it? So that's the question. So the question is, do ResNets converge in some sense? And if yes, in what sense to neural ODEs? Well, if you look at it from purely numerical analysis perspective, what we know is that if you put some conditions on these coefficients, relating these discrete coefficients to these functions down here. So if the AK are the samples of A bar at some point K over L, same for B, and then this coefficient in front has some scaling like 1 over L, then, well, this is, we're a well-known territory, at least we think we are. So this is an Euler scheme, and it's known that under some conditions on the coefficients, there is a unique solution for the ODE, and we do indeed have convergence of the solution of the discrete dynamics of the hidden state to the ODE. But so here, and in fact, this was studied in detail in the paper by Thorpe and Van Gennep, where they actually showed more than this. They showed that not only, well, it's well known that this discrete system will converge to the ODE, but what's more interesting in the paper is that they show that there's a gamma convergence. So in fact, if I optimize over the solution, the coefficients of the discrete equation, I converge to the solutions of a limiting optimization problem, which corresponds to the optimal control problem and optimization over the ODE coefficient. So there is more than just a simple convergence, but what's the ingredient used here is that this is an ansatz. So you have to assume the scaling behavior, equation 3. And of course, in practice, we don't get to choose the scaling behavior because the weights result from training. So we have some data, and then what this ansatz really means is that we're saying, well, now we train on the same data set, networks with larger and larger number of layers, and we expect the weights to behave in the same way according to when we change the number of layers. This is really non-trivial, so it's not clear why they would follow this ansatz rather than some other ones. And there's very little work. In fact, until recently, we thought there was no work on this until my good friend Human Oadi was here. He sent us his very interesting paper. So there's some work on this. So it's a non-trivial problem to derive the scaling properties, the asymptotic behavior of the trained weights from, well, some properties of the data, and then some assumption on how they're trained. You have to specify how they're trained. It's a gradient dynamics or stochastic gradient dynamics. So deriving the scaling properties from the problem is non-trivial. And it is not clear, in any case, if the trained weights will, in all cases, behave like this ansatz. Okay, they may or may not. And we'll see that in some cases they do, in some cases they don't. And it's interesting to see what that depends on. So what we are interested here is to investigate the actual behavior of the trained weights. Actual meaning when we do actual training, we do a detailed numerical experiments of various architectures, realistic architectures, and see how do these train weights behave? Do they behave like this ansatz I showed, or is it different? And what we do see is that in the different architectures we studied, we identified 3 different scaling regimes depending on some features of the network architecture. So one of the regimes does correspond to an ODE limit. Another regime corresponds to a stochastic differential equation limit, a diffusion limit. And a third one corresponds to a sparse limit, which in fact has been studied a lot in another strand of literature on neural networks, not on ResNets, but there is a whole strand of literature on convolutional networks, which is very focused on this sparse limit. I refer here to the work of Stefan Malin and co-authors. So, and we do recover here a sparse regime. So I'm not going to talk a lot about sparse regime unless there's some interest in that. But so we see at least 3 different scaling regimes in the limited experiments that we've done. And I'll try to describe a little bit what we see and what does that mean. Okay, so let me show you some results to start. So I'm going to describe a bit more the architectures, but basically most of the things I'm going to show are for fully connected layers. So there are no restrictions on the matrices A and B. They can be fully populated. I will not show here the convolutional case because it requires me to show too many graphs, but let's focus on the fully connected layer case. So the first thing that we see, so what we do here is this, we're gonna take different data sets. Some of them are simulated data sets, some of them are classical data sets used in deep learning. For example, here I'm gonna show you MNIST, the handwriting database that is used in a lot of examples. And there's a third example with images that I'm gonna show you later. So we take one of these data sets, which are fairly large, and then we train a ResNet on it with a given depth L, and then we change L, we retrain, and we retrain until we reach the same accuracy for all levels L. I'm going to describe a little bit more later. And we look at how the properties of the train weights change with L. So that's all the graphs I'm going to show you will have the depth L on the horizontal axis in logarithmic scale, and some quantity related to the train coefficients on the vertical axis. So the first thing that we see is that the trained weights vanish as the number of layers increases, okay? That shouldn't be really shocking because if you're fixing the input and the output, and then you are learning a map, and this map will be the composition of L ingredients, L maps, and the map is fixed, and you're increasing the number of ingredients in the composition. So you would expect, unless there's something very inhomogeneous going on, that if all the layers have the same magnitude in terms of coefficients, you would expect each component to go to 0. Because if you compose them and the composition is finite, then either you have to have a non-uniform scaling, some of them have to vanish, others may remain finite, that's a sparse limit, or you have to have that all of them vanish, and in fact, they have to vanish at a specific scale. So that's what happens, and that means that the coefficients, the trained coefficients will become smaller and smaller. You get closer and closer to the identity at each layer. So you're gonna have a perturbation of the identity with some power of L. And that's what we see. So if you, for example, so we had these coefficients inside and the other coefficient delta L outside, they vanish as L increases, they become smaller. Okay, this again not shocking, but remember that this is not the ansatz used in the neural ODE, because in the neural ODE, you have finite a limit for the coefficients, okay? So in some cases, like if you have ReLU, if you have a ReLU activation function, it's homogeneous of degree 1, so you can absorb, you can bring the outside weight inside. So you can say, well, we only look at the product. I'm going to show you that. But in this case, this is the case of tan H. This is a smooth activation function that is not homogeneous of degree 1. Well, actually, the weight outside and inside play different roles. So, what we see is that you don't see the ansatz that I showed you earlier. Okay, and then if you look in the ReLU case, it's even more disturbing because if you, well, first of all, what we see is that, so this is a sample of weights. So this is an unusually deep network with 8,000 layers. You don't really use that, but it just to show, what happens when you increase the number of layers. Well, this is a sample set of weights where the horizontal axis is now the layer. So the layer 0, 1, 2 to 8,000. And this is just displaying one of the weights. So you just take one of the weights in the matrix, say weight 8, 4. So it links the neuron 8 to neuron 4 in the next layer. And what you see is that as a function of the layer, it really doesn't look like a smooth function. It really looks like something like a white noise or some noise. It's not actually not like a white noise. It looks like a pretty complicated noise, but it looks like a noise type object rather than a smooth function. So this shows us that there's something else going on when you use a ReLU activation function rather than a smooth activation function. And now if you so in fact, here on this graph, I compare the two. So again, it's the same data set, but you train ResNets, again, the same architecture, but then you have different activation functions, tanh, smooth one on the left. And then in the middle, you have ReLU, non-smooth one. And you see that if you plot a given weight as a function of the layer, well, in the tanh case, you get a smooth dependence. In the ReLU case, you get some kind of white noise type dependence. Okay, so clearly the asymptotic behavior of weights does seem to depend on something, at least the activation function. And note that in these examples, both networks are trained on the same data and they attain the same accuracy at the end of the training. So we're not looking at uncomparable things. They are comparable in terms of output. Now, this is a horrible graph in the middle. If you're not used to looking at pictures of white noise like me all day, you don't like these graphs. So what you do with white noise is you resum them. So if you do the cumulative sum of these things, so that's a very unnatural thing to do, you are taking the weights at layer J, and then you sum them for J equals 1 to K. So, and then what's displayed on the last graph here on the right is the cumulative sum of the trained weights for the ReLU case. Now, the cumulative sum now looks nice. It looks like a continuous path, but it looks like a diffusive path. So it looks like some Brownian function or something of that sort. So it looks like an irregular path, certainly not smooth like the one on the left. So what do we see here? What we see is that, well, with a smooth activation function, it seems like you get smooth weights. With a non-smooth activation function like ReLU, non-smooth at 0, I mean, it's smooth elsewhere, but at 0, it's you get these noisy weights. And if you resum them, so if you take the cumulative sum of the weights from layer 0 to K, which is a natural thing to do because this thing never appears anywhere, right? Then you get something which looks like a diffusive path. Okay, very, very bizarre. And you can now look at these paths. You can say, well, if I resum, like the gentleman says, the weights from layer 0 to K, what kind of path am I getting? Well, one way to do this is to look at the quadratic variation of this path. So basically means the L2 norm of the weights, because you sum the square of the weights, which is sum the square of the increments of this path. And this thing is what I was showing here. You can see that this thing actually is pretty stable as the weights, as the number of layers increase. So it seems that the noise hypothesis is not a stupid one. It does seem to describe what's going on. Okay, so that's some preliminary results from the numerical experiment. So having seen this, we say, okay, well, what are we seeing here? What we're seeing here, and we did more experiments than this, that's in the paper, but so what we see here is that basically are the results of the numerical experiments describing the deep network behavior of the trained weights seem to fall into two classes. One is what we call hypothesis one, is that the weights shrink I mean, in all cases, the weights shrink to zero, and they shrink to zero as, let's say, like some power of the number of layers. Let's call this power of beta. And in the first case, it seems that they shrink to a smooth function. So if you blow them up at the right scale, you're going to see a smooth function. And if you forget the scaling, this is what's basically the ansatz in the neural ODE literature, because you want the weights to be sampled from a smooth function. And this would be exactly this with no scaling factor in front. But since the weights shrink, we say, okay, well, let's just blow them up at the right scale, which is the scale at which we see them shrinking. And then if the limit is smooth, then we'll say we're in the case one. And in fact, that's what's shown here. These are actually blown up weights. I mean, they're not blowing up. I'm blowing up the scale for you to see what's going on. And of course, I can do this. I can plot them on any scale I like, and the smoothness will be by the property that I want. Okay, so this is case one, or hypothesis one. And the second case is that, well, we see that there is something else going on. There's some noise term. And the noise term, I mean, we don't need to introduce a probabilistic notion of noise term. We're just saying, well, what we see is that there are noise-like a behavior as a function of the layer. What does that mean? What it really means is simply that if we resum them from layer 0 to k, then we get a function that is irregular. So if you call this function W, then it means that the weights are the increments of some function W. And W can have a non-trivial scaling limit as a function, but A doesn't, because they're increments of a function over a shrinking time interval, so that they will give you something which does not have a limit as a function. Okay, fine. And you can include a term like the first one. You can combine the two. Okay, so these are the two hypothesis. And what we show, I describe it a little bit how we show this, is that you can actually show that all the numerical experiments we have fit either with one or the other case, or a third case, there is a sparse limit. Sparse limit meaning most of the coefficients go to zero and only a finite number will be non-zero but have finite value. So I'm not going to describe that one. There's a hypothesis 3 that is the sparse one. And we can ask, so how do we show that these things hold? Well, so the weights are, you can see them as a function of the layer. So we're going to look at the behavior under scaling when the number of layers changes of various discretized norms. And basically the roughness or smoothness of the weights will depend on which norms blow up as L goes to infinity, which norms remain finite, which norms shrink to zero. So we kind of detect in which space the limiting function A bar falls into, okay? And so here are some of the norms that I already showed on some of the plots. So we can look at the magnitude of the weights. That's just the soup norm. And these are matrix weights. So F denotes the Frobenius norm for the matrix. You can, in the noise scaling case, we look at the cumulative sum and then take the norm or the soup norm. So that's the case where you have individual weights can blow up, but then the cumulative sum is nicely behaved. And then you can scale both of these things by scaling factor L to the beta. And we also look at the norm of the increments. So this is, I talk about resumming, but if you look in the literature, especially in the paper of Thorpe and Van Gennep, they look at the case where in the training you use a smoothing norm, a Sobolev smoothing norm, which requires that the increments of the weights have a finite L2 norm. So we also look at this to see if it's finite or it explodes. And finally, we look at if again, I showed you that if you sum the coefficients up to layer k, you get a function that looks like a diffusion. This would imply that the sum of increments of this diffusion, meaning the sum of the squared weights, would be finite. This would correspond to the quadratic variation of the cumulative sum. And so we also look at this. So how do we do this? Well, basically, it's it's a regression on the results of the simulation. So all of these, the hypothesis 1 and 2 that I presented are additive decompositions, either with a noise term or without a noise term. So you can see this estimation of the components of this decomposition as a regression. And then you estimate the coefficients, the magnitude of the coefficients in the regression by looking at a log-log plot, a logarithmic regression of the soup norm of each term. So to estimate the scaling exponents alpha and beta. Okay, again, nothing really extraordinary here, but and in this way, especially by looking at this quantity here, you can also get, so this is trying to estimate the Holder regularity basically of the limiting function A, because if A has Holder regularity beta, then basically this increment will be of the order L to the minus beta, and so this will have a finite limit, otherwise it goes to 0 or infinity. So we try to estimate the Holder regularity of the limit as well. Okay, so and then in the noise case, we try to estimate the regularity of the resummed coefficients, which gives us and to see in particular if it has finite quadratic variation, which would correspond to the diffusion limit. Okay. So what do we see? Again, I'm not gonna give you too many graphs, but basically what we see is evidence consistent with the fact that, well, let me distinguish here again the two cases: a smooth activation function and ReLU, non-smooth activation function, non-smooth at 0. So in the smooth case, what we see is that, again, the weights shrink, as we said, as some power of the depth. And the limiting object, if we try to estimate its Holder regularity using the scaling of the increments, it corresponds to something that is roughly 1/2 Holder regular. So the estimate exponent beta is close to 1/2. Okay, so then what else? Well, in the ReLU case, on the other hand, we don't get really a smooth coefficient. What we get is this noise scaling that you saw. The weights don't look like a smooth function; they look like increments of some function, and this function appears to have non-zero quadratic variation. Again, if you look at its quadratic variation norm, which is it's L2 norm of the coefficients, this has a stable behavior. It doesn't explode or go to 0 as you scale, as you increase the depth. And again, this is for both for the simulated data, MNIST and unImagined. Okay, so these are basically the numerical experiments which indicate that there seem to be more than one scaling regime, and there's one where you have smooth limit, the other one have non-smooth limit for coefficients, which is really a noise limit. You have to resum them to get a function. And now we want to see, well, if we go back and revisit the asymptotics of the deep ResNet under these different scaling regimes, what do we get? Well, let's look at this now. So, well, hypothesis 1 is you have up to a scaling, you have in fact a smooth limit. So the weights are in fact a scaling factor times a smooth function of the layer, both for A and B. And all of these weights can vanish as L goes to infinity, except in the case where beta is 0 and alpha is 1. In that case, we're back in the case studied by Thorpe and Van Gennep, and in that case, the weights do not vanish; they tend to a smooth limit. It's a finite limit. Okay, but in general, as we'll see, it's not. You can embed the scaling, coefficients here and study the limit in the same way as they did. And here I'm going to look first at the smooth activation function case, which I believe is also the assumption they make. So here I'm going to need to assume that the activation function is C3, 0 at 0, that's always possible, and then it has a bounded third derivative. This is for technical reasons. Okay, so again, the scaling regime is described by two exponents, alpha and beta. Alpha is the thing outside the activation function, and L to the minus beta is inside. Okay, well, just let me recall the, well, first of all, we can recover what is already known from the paper of Thorpe and Van Gogh, although, I mean, they do much more than this, but this is part of what they do, that if alpha is 1 and beta equals B0, then we have a Euler scheme of an ODE, and under some assumption, for example, if the ODE has a unique solution, this is the case if we have a Lipschitz activation function, and if the coefficients here have some smoothness in the paper of Thorpe and Van Gogh, if they actually have Sobolev regularity, then the hidden state dynamics converge uniformly to the solution of this neural ODE, in the sense that you have the hidden state minus the interpolated hidden state minus the solution of this will go to 0 as L goes to infinity. So that's known, and we can recover that as a special case here. Okay, but this is very special case where alpha is equal to 1, and there is the weights do not shrink, non-vanishing weights. And as I showed you in the numerical experiments, we don't really see that, at least for the architectures that we have. So what we do see, if you pay attention to the graphs, what we do see is that alpha and beta are somewhere in between 0 and 1, but both of them. And in fact, the sum is close to 1 for reasons that you will understand when I describe the limits. The sum is close to 1, but each of them can be different from 0 and 1. So in that case, the weights shrink to 0 with some speed, L to the minus beta, and the limits may be smooth. So we're still again in the smooth activation function case. But because the weights shrink to 0, you can see that now the activation function we only care about the activation function near 0, because the weights, what's inside the activation function is shrinking to 0. So unless the hidden state explodes, which these assumptions guarantee it doesn't, the argument of the activation functions shrink to 0. So all that matters will be the behavior at 0. And in fact, all that will matter is the first order expansion of this activation function at 0. So in fact, the limit will only depend on the slope. And this is in fact not shocking because there's a lot of literature suggesting that the activation function doesn't really play a big role as long as, you know, there's some properties, qualitative properties. And here it shows that it really doesn't play a role in the large L limit. It's only the slope plays a role. So, but this is not very nice because you can see that this is a linear system. So it doesn't seem like the most expressive ODE you would like to have. So it shows that, you know, if you just scale the number of layers to infinity, this doesn't look like a very interesting architecture because you get a linear ODE as a limit, and the linear ODE will give you a not very expressive input-output function. So I don't really need to have a deep ResNet to give me a linear ODE. This doesn't seem a great idea. So it seems that the previous limit where you get this full nonlinearity of the activation function is really special. And the generic case, which we do observe, is giving us this linear limit. This doesn't seem, so it means that in particular, the shallow, I mean, the low number of layers is probably expected to perform better than increasing L to a very large number, because if this is the limit, that's not great. So now let's look at the other scaling limit with where in the case where the weights have this white noise term in them, or the noise term in them. So in fact, we're not assuming it's white noise. We're not assuming independence at all, and they don't look independent in the data at all. But what we are assuming is that the weights they behave like the increments of some function, WA dot WB, plus eventually a smooth term. But this term will change everything. So if we resum the weights, then we get W, but we don't get to resum them because the weights are here inside the activation function. So I can't really resum them. And we're not going to assume these things are white noises. We're going to assume that they are increments of some Ito process. They can have complicated dependent structure in time, and they have a Holder regularity. So these are increments of functions with some Holder regularity, which is lower than 1. It can be 1/2 if you think of 1/2 a minus if you think of Brownian motion, but they don't have to be that. So so in this case, we're going to look at, in fact, the case where they're 1/2 a minus, so they're Ito processes. So think of a Brownian motion or some diffusion. And what we'll see is that in this case, the asymptotic limit will, but the asymptotic behavior will depend on the quadratic variation of these two functions, W and WB, which again, you can think of as the L2 norm of the weights in the discrete case. You sum the increments of W, but the increments of W are these weights. You sum the weight squared, you get the quadratic variation. So think of the limit of the sum of weight squared as the integral of some function sigma A or sigma B. This is the quadratic variation of the function, the W. And I'm going to define a quadratic form, which involves these coefficients, sigma A and sigma B. And this is going to play a role in the limits. So let me now show you the limits. So what we show is that in the case, so now I'm going to look at the other case where alpha is equal to 0. So there's no coefficient outside, and you put everything inside. So in the ReLU case, you can do that because you can always move the coefficients inside because it's a homogeneous activation function of order 1, but not in the general case. But let's assume that there is only scaling of the coefficient inside with the exponent beta. In this case, what we show is that this hypothesis 2, the scaling under hypothesis 2, leads in fact to a different limit. So it's a differential equation which is being now driven by this irregular or rough input term WA and WB. So if you think of WA and WB as a random process, as some Brownian motion or some diffusion, you can think of it as a stochastic differential equation, but you don't really need to think of it as a stochastic term. You can think of it just as an irregular function of the layer. It still makes sense in some sense. So what's the structure of the equation? Well, it's really simple. It's an additive multiplicative equation. So there is this trace of the activation function just to the slope at 0. Again, the weight shrinks, so only the behavior at 0 of the activation function will matter here. But now you have this interesting term. It's an additive term plus a multiplicative term. And so this looks like a very simple, differential equation or stochastic differential equation. But actually, by combining this additive and multiplicative term together, you can get a wide variety of input-output maps when you go from 0 to 1. So this is looks like a deceivingly simple structure. In fact, it's a highly expressive structure in terms of the kinds of maps you can generate by choosing the coefficients here. And then there's a third term that stems from the non-zero quadratic variation of the coefficient, the irregularity, and that's the Ito term. So here we have to expand to order 2, and the order 2 term doesn't vanish because of the property that the sum of squares of the weights do not vanish. Then you get this third quadratic variation term. So now if you think of the simplest case where now this may seem a strange asymptotic limit, but in fact, if you think about how most neural network trainers are optimized, well, they're optimized typically by choosing independent, identically distributed weights, often drawn from a Gaussian distribution. That corresponds exactly to the case where the AKs are independent, and if you draw them from a normal distribution, you scale them appropriately, then it means that the W's we're talking about here are really Brownian motion. So the initialization used by most training algorithms for neural networks actually correspond to picking a W that is exactly a Brownian motion. So the case where W's are Brownian motions is in fact not very strange. It's implicitly used at all initializations. But in that case, you then actually have a stochastic differential equation where you can now identify the randomness of the Brownian motions here as the randomness of the initialization. And in fact, you see that you have a quadratic SDE, you have a quadratic stochastic differential equation. This term is quadratic. And that's not very nice because quadratic SDEs can blow up. So it can blow up before you reach the output time 1. So there is an assumption here that the thing is not blowing up. So if this thing does not blow up, which is an implicit condition on the weights here that define WA, WB, then we can show again that the hidden state dynamics converges uniformly in L2. This is a strong convergence. But it may be the case that it blows up, and you can discuss the conditions under which it doesn't blow up. So if it does blow, it means the training doesn't work. It doesn't converge. Now, as I mentioned, the case of independent weights does also lead to this limit. And in fact, Peluchetti and Tavarro studied in a paper in 2020 in some other conference. It's not ICML. I think it's not sure which one was that was. They proved the weak convergence of the deep of the ResNet to the SDE limit, where the W's are in fact exactly Brownian motions, in the case where the weights are independent. But of course, this only applies at initialization, and when we train the weights, we cannot expect the trained weights to be independent across layers. They're actually not, and any test of this in the simulations gives you will fail. Also, here it's important to understand in what sense we're talking about convergence. So the randomness. So we were talking about stochastic differential equations. The discussion about initialization should put you on the lead that the randomness we're speaking about, or the probability space these things live on, is in fact the probability space defined by the initializations. That's the only random ingredient we input to the training. Once we initialize the weights, then it's a gradient-based optimization going on data, given the data. So it means that the correct way to think about the convergence to the deep divergence limit, in my opinion, is to look at strong convergence, because weak convergence, as studied in some other papers, really means that you are going to retrain the network with different initial weights independently, and you're going to average your outcomes across many different trainings. That's not what people do, really. They just train it once. So what they want is a strong convergence, or even almost convergence for a typical training set. So this is what we study. So now, are these limits real? What does that mean? Well, as a mathematician, you prove a theorem, it's done. Bye. But when we presented these things in some venues, people say, well, but is this real? Does this actually correspond to the behavior of deep networks for reasonable depths? And it is a reasonable question. So we show here on this graph, we look at the different scaling regimes. This is under hypothesis 1 with the tan H. We look at the convergence of the network output to the ODE limit in the case where the assumptions are satisfied. So it means we want to see if for reasonable depths does the output function correspond to what the ODE limit predicts. So the tests show that it is indeed the case, both in the diffusion limit and in the ODE limit. If you compare the actual output of the network with what is described in the asymptotic limit of the ODE or SD, you do actually have a good description. You don't need to go to a million layers. It's already the case with 1,000 layers. Okay, so I'm nearly out of time, so let me end with a small discussion. So up to now, I've been describing the asymptotics of the hidden layer. But of course, when you're doing training, you're also interested in the gradient. What's the gradient? Well, you have some loss function f that you use in the training, and the hidden layer propagates forward, and you take the gradient of the loss function at for each set of layers, and the way you do it, you use back propagation. The gradient of the loss function propagates backwards. And also the loss function itself can be propagated at the same time backwards. So this, of course, can also be described in the ResNet architecture. So the backward propagation of the gradient with the back propagation algorithm corresponds to an iteration through layers going backwards, starting from a determinant value, that is the gradient of the loss function at the output state. And at order 1 in the depth, if you take the equation, the back propagation equation, and then expand it, you do a Taylor expansion of order 2 of the activation function, assuming again a smooth activation function, well, the slope, it will give you this. It will give you a linear term, and then you get this the second term from the second order term. This is a quadratic term, and then higher order terms in L. So this suggests that we can also describe under the same asymptotics not only the dynamics of the hidden state, but also the backward dynamics of the gradient of the loss function, which is the interesting thing for training. I mean, it's an ingredient that's used in training. And a very loose analysis here suggests that this is going to solve a backward stochastic differential equation, whereas the hidden state, as we saw, will solve a forward stochastic differential equation. So in the diffusion regime, in the second regime, we will therefore have the hidden state solving a stochastic equation going forward, and then the gradient will solve a stochastic equation going backward, which is coupled to the first one. And it will start from the terminal condition, that is the gradient of the loss function at the output state, and then go backwards. Well, so this is a loose analysis, but in fact, a more careful analysis should take into account of the fact that we are mainly interested in the behavior of these quantities at optimality. So at after training. So one can more generally study the behavior of these weights and the gradients under training. So this is, in fact, if I understand correctly, this is partly what is done in Humanoides paper. But here, if we say, okay, let's assume that we did the training, it works, somebody parachuted us at the optimum. Well, then there's some special relations which come out, and the special relations will imply that the weights are in fact at the optimum of the loss function, and where you have trained and this will be a function of the forward equation, the solution of the hidden state. And so this leads us to the following backward stochastic differential equation for the gradient. in which you have, again, the same term that you had, by the gradient now of the term that you had in the dynamics of the hidden state, but now this was a quadratic term, so now this is a linear term. And then you have an extra linear term which comes from the optimality, okay? So here this gives us, so this is to be linked to what you see, for instance, in the literature on the training of the neural ODEs. There's a lot of literature, there's a lot of work by and collaborators who look at the training of the neural ODE as an optimal control problem. They look at the HAB equation and the optimality conditions. So here in the diffusive limit, you have a similar relation, but now it leads to a system of forward-backward stochastic differential equations, where the randomness here, again, you should think of it as a reshuffled version of the initialization weights, which leads to the stochastic term here. Okay, I think I'm out of time, so I'm going to stop here. So what I tried to describe is some evidence from numerical experiments which try to describe the scaling behavior of train weights in these deep ResNets. So we see three different scaling regimes. I described two of them. The third one is a sparse one. They're described more detail in the paper. And then what we show is that depending on which scaling regime you are in, you can obtain an ODE limit or a stochastic differential equation limit in which the stochastic term should be interpreted as coming from the randomness in the initialization of the weights. And in all cases, we're able to show strong convergence to these limits as the number of layers increases under these scaling assumptions. And the numerical experiments on deep ResNets with around 1,000 layers confirm that this is indeed what we see. We're not, it's not something which is so remote that you never observe it. And in the stochastic case, we show that you also can obtain the dynamics of the gradient with respect to the hidden state, an object that is described typically in terms of back propagation, and here it's described in terms of backward stochastic differential equation coupled to the hidden state. So some of this is described in more detail in the ICML paper, and we have a forthcoming work in which we describe the last part, the link with backward-forward stochastic differential equations in more detail. I guess I can stop here. Thank you.